Hey everyone, and welcome to this explainer. Today, we are unpacking a really fundamental shift that's happening in artificial intelligence right now. So we're transitioning away from those solo chatbots, the single assistants we've all gotten completely used to. And we're moving straight into the era of fleets. We're talking about entire teams of AI agents working together to solve really complex problems. Now, it's an absolutely incredible leap forward for sure, but it brings up this massive friction point that is quietly breaking systems behind the scenes. And that friction point, it's memory.
Just to give you a sense of the sheer scale of this transition, check this out. According to a report by Xylos Research, Gartner actually measured a massive 1,445% surge in multi-agent system inquiries from early 2024 to mid-2025. I mean, the demand is just explosive. Literally every enterprise out there wants a coordinated fleet of AI agents handling their workflows. But, we have to contrast that explosive growth with this pretty harsh reality. Up to 87% of multi-agent large language model systems still fail in production. Just imagine that for a second. You invest in this cutting-edge team of AI agents only to have nearly 9 out of 10 deployments completely break down the second they hit the real world. That is a staggering failure rate, and we absolutely cannot ignore it.
Okay, so let's dive into this and look at our roadmap for solving this crisis together. We're going to cover 1. The multi-agent memory crisis, 2. Context to distributed systems, 3. The 4 memory failures, 4. Architecting governed shared memory, and finally, 5. Real-world workflows and testing. Let's get right into it.
Section 1. The multi-agent memory crisis. Surging demand versus high failure.
Moving right along to Section 2. Context to distributed systems, from chatbots to teams.
To set the stage here, Anthropic's own evaluations actually show that multi-agent setups outperform single-agent setups by over 90% on research tasks. So, the potential is undeniably there. But they're bottlenecked by those catastrophic failure rates we just talked about. So what's actually breaking? Well, when we scale up, we have to completely rethink what AI memory actually is. Xylos Research found that 79% of multi-agent system failures are rooted purely in coordination issues, not underlying technical bugs. It's not like the AI models are losing their reasoning capabilities or glicking out. No, the failure lies entirely in how these agents coordinate their shared state and how they communicate with one another.
Actually, the core thesis for this entire crisis boils down to this really fascinating quote from a recent arXiv paper. It says that when you move from one user talking to one assistant to a whole fleet of interacting agents, memory is no longer just a context window problem. Meaning it's no longer just about how much text the AI can read at once. It becomes a governed, distributed systems problem. It's all about synchronization, consistency, and access control.
Because of this, operators are now forced to make a huge architectural choice. On one hand, you've got shared memory. This is where all agents read and write to a centralized repository that acts as a single source of truth, giving you incredibly low latency coordination on the exact same data set. On the other hand, you have distributed memory, which gives each agent its own isolated local repository, and they only communicate through network message passing. That gives you high isolation, sure, but it adds network latency and a massive risk of synchronization drift. The agents can literally fall out of sync with what the others know. So for tight collaboration, shared memory is absolutely essential, but it requires some serious management.
Which brings us to Section 3, the 4 memory failures. What goes wrong when agents share data?
Researchers have categorized these system breakdowns into 4 highly destructive modes. Failure, number 1, is unauthorized leakage. Imagine a customer support agent querying the shared memory and accidentally pulling up highly sensitive billing notes that were meant only for the finance agents. Because traditional vector databases retrieve data based purely on semantic similarity, meaning they just fetch stuff because the words have a related meaning, they will happily serve up private secrets if the query matches the text. That's a huge security and privacy failure. Failure number 2 is stale propagation. This happens when updates just fail to synchronize correctly across the agents. Like say, one agent updates a user's shipping address in the system, but a network lag means another downstream agent goes ahead and executes a shipping workflow using the old, outdated address. You end up with contradictory actions and totally degraded operational stability. It's a real mess.
Third, we've got contradiction persistence. A lot of these systems rely on append-only databases without any explicit rules for replacing old data. So if Agent A writes that a user's preference is dark mode, and later on Agent B writes that the preference is light mode, both of those mutually incompatible facts just sit there, endlessly coexisting in the database. Any downstream agent trying to read that history has absolutely zero way of knowing which fact is the actual truth.
And finally, number 4, provenance collapse. This is when an agent retrieves a fact, but the system can't trace it back to the original writing agent, the source system, or even the timestamp. Without that provenance, debugging a multi-agent system basically becomes total guesswork. You lose your audit trail, and any governance guarantees you had become completely unverifiable.
Section 4. Architecting Governed Shared Memory. Building the solution. Okay, so how do we cure these 4 massive failures? We have to build what's known as governed shared memory. This architecture tackles the unauthorized leakage problem head-on by implementing strict memory scopes. Instead of just a flat database, memory is scoped into strict tiers: agent local, team shared, tenant global, or restricted by explicit policy. This guarantees that semantic similarity alone is never going to bypass your policy constraints. The system doesn't just ask, hey, was this data relevant? It asks, is this specific agent actually authorized to see the specific version of the data?
To fix those persistent contradictions we talked about earlier, systems need to apply 3 main tactics, highlighted by the GoClaw blog. First, strict access granularity, so dictating exactly who gets to write to core memory in the first place. Second, timestamping and semantic versioning, which lets the system track how information mutates over time. And third, this is kind of my favorite, when agents still end up arguing, you deploy a manager agent. This is basically a higher-tier AI, whose only job is to play referee, evaluate reliability, and just discard opposing reasoning flows.
Now, structurally, modern platforms like GoClaw organize all of this into a 3-tier memory hierarchy. At the top, you have the agent I/O layer, which ingests all kinds of messy, raw data from the outside world. Below that is the agent cache layer, handling your short-term context. And finally, at the base, the agent memory layer, which is the persistent vector database. This hierarchy is absolutely crucial because it filters out the raw, noisy data before it ever hits the long-term persistent layer, which totally prevents context window overflow.
All right, Section 5, Real-World Workflows and Testing, putting it into production. Let's tie all of this theory together and look at how it functions out in the wild. This workflow brilliantly illustrates something called dynamic reasoning alignment. Imagine you have an agentic workflow with a coder and a tester. The coder agent finishes a Python module and writes the draft into shared memory. The tester agent then fetches it, runs its tests, detects an error, and writes the error log directly back to that exact same shared memory space. Then the coder just reads the log and resolves it. Notice what they didn't do. They never pass raw source code back and forth through expensive API prompts. They just update the shared memory. It saves massive amounts of tokens and ensures one single source of truth. It's brilliant.
But hey, we need to prove these architectures actually hold up under pressure, right? So, the arXiv researchers built an open-source evaluation harness called arXiv. They used it to systematically probe a live, production multi-tenant memory service called memclaw, basically pushing it to its absolute limits across all the governance dimensions we've been talking about today.
And you know what? The test was incredibly revealing. On the positive side, provenance tracing was perfect. They hit 100% complete end-to-end chain reconstruction. No way! But this is exactly why live testing is crucial, because it catches things theory misses. arXiv actually caught a real-world subtenant leakage gap on a direct get-by-ID access path. Luckily, it was immediately remediated by the operator. It also exposed a really fascinating pipeline issue. A synchronous deduplication gate can actually starve the contradiction detector. Essentially, because contradictory statements look so textually similar, like saying a car is blue versus a car is red, the system was just rejecting them as duplicates before the contradiction detector even had a chance to evaluate them.
So, what does this all mean? These findings prove that as we move to fleets of interacting agents, long context retrieval alone just isn't going to cut it anymore. I want to leave you with this final provocative thought. If your multi-agent system lacks strict access controls, temporal supersession, and unshakable provenance, it is just a recipe for disaster waiting to happen. So you've got to ask yourself, is your AI just remembering, or is it actually governing? Thank you so much for joining me for this explainer, and I will see you next time.